Good afternoon. Okay, so we are now going to shift into the concept of factoring. Factoring. We're going to factor polynomials in a minute, but first I want to back up and talk about the whole concept of factoring anything. Why do we do that? So back in elementary school, you probably were shown how to factor just a plain old natural number like 36. And maybe you were shown, not everybody's shown this method, but maybe you were shown to make a factor tree. So you think of two numbers that multiply to 36, like 9 and 4, and then you look at 9 and 4 individually and see if they can be factored any further. 9 is 3 times 3, and 4 is 2 times 2, and once you reach prime numbers in all of these branches, you're done with the factoring process. And then you can state that 36 is equivalent to 3 times 3 times 2 times 2, which we can write in exponential form, 3 squared times 2 squared. So why do we do that? We do that because while 36 is a very understandable, attainable number for us to use, that's not the DNA of 36. The DNA, what makes up 36, the essence of 36, is this product. The product of 3, 3, 2, and 2. That is the essence of 36. If you break it down to its molecular foundation, that's what it is. If you break any person down and look at their DNA, you will see the DNA, the little pieces of DNA that make up that person. And that's what we're doing when we look at the factorization of a number. We're looking at the essence of that number. There is no other number in the world, even in the universe, that has a DNA of 3 squared times 2 squared. 3 squared times 2 squared can only equal one number, 36. The DNA in you is what makes you, you. The DNA, the way it's put together in you, can't produce any other being in the universe, except maybe a clone. So that's why we factor, to see the essence of a number. Okay, so if we can factor a number, we could factor a pair of numbers. So let's take the number that we just used, 36, and let's take another number. Let's take 48. Now I haven't factored 48 yet, so let's do that now. 48, 6 times 8, I can keep going. 3 times 2, and 8 is 4 times 2, I can keep going. So 48 is 2 to the 4th times 3. That's its DNA. Now let's look at these two different DNAs. What do they have in common? Well, they both have some 2's. Well, how many 2's do they have in common? 2 2's over here, and we have 4 2's over here. So at most, they have 2 squared in common. Now let's look at their 3's. 1 3 here, 2 3's over here. So at most, they have 3, a single 3 in common. So if this is what they have in common, this is the DNA that they share. We call this the greatest common factor. We maximized the number of each type of prime number that they have. I could have said that they have a single 2 and a single 3 in common. That is true. That's not a lie. They have a 2 and a 3 in common. But that's not the most that they have in common. Sometimes we just want any common factor for whatever purpose, but sometimes we want the greatest common factor. And in this case, the greatest common factor is 2 squared times 3, or 12. So 12 is the GCF of 36 and 48. And what is the GCF good for? Well, one simple, easy to remember use of a GCF is if you have a fraction, if you know the GCF of the numerator and the denominator, you can reduce that fraction quickly. I can just divide the 36 by the GCF, which we now know is 12, and get 3, and the denominator by the same GCF, and get 4. So GCF helps me reduce fractions. There are many other uses. That's just the first one that comes to mind. Okay, so now you've seen what one purpose of factoring is and what the essence of factoring is. Now we're going to apply the same thing, the same discovery of greatest common factor to monomials. So let's say I have the monomial 8x to the 5th and the monomial 6x to the 7th. I want to know what the GCF of those two terms is. What factors do they share? And I want to maximize that factor that they share. I want to find the greatest common factor, because maybe I have a fraction like this and I need to reduce it. So how do I reduce it quickly? Okay, so as you know from seeing monomials before, monomials have two parts, the coefficient and the part with the variable raised to an exponent. So for the purposes of trying to find the GCF, I'm going to think of each term as those two parts, the coefficient part and the variable part. So I look for the GCF of the coefficient part first. 8 and 6. What is their GCF? Well, 2 goes into both. 4 goes into 8 but not 6. 3 goes into 6 but not 8. So the best I can do is 2. Right? I could do a little factor tree if I wanted to. I get 2 times 2 times 2 here and 2 times 3. So the most they have in common is a 2. So I know my GCF is going to have 2 as the coefficient. And now I look at the variable part. I have x to the 5th here. I have x to the 7th here. So the most that they have in common is x to the 5th. To visualize that, here are the 5 x's from x to the 5th, and here are the 7 x's from x to the 7th. What do they have in common? 5 x's multiplied, right? So the GCF is 2x to the 5th. Now let's try this again with something more complicated. I can throw in a second variable in there. A y. So one monomial I'm making 4x cubed y squared, and another one I'm making 12 x squared y squared. Okay, the coefficient part, 4 and 12, the GCF is 4. Now I go through each variable one at a time. The x's, GCF is x squared, and the y's. The exponent of the y's is exactly the same, so that is the GCF. 4x squared y squared is the GCF in this case. Two x cubed, 3y squared. We're searching for the GCF. Now you'll notice 2 and 3 are prime, so they don't share any factors. And the variables are different. I have x's here and y's here, so they don't share anything either. So there is no GCF in this case. Numbers don't always have GCFs. Like a pair of prime numbers are not going to have a GCF. Monomials don't always have a GCF either. Okay, now polynomials have something that just a pair of numbers doesn't. Polynomials have another use for the GCF. You can use the GCF for more things than just reducing a fraction. Because we can take two monomials. I'll take the first pair that we had, 8x to the 5th and 6x to the 7th, and I can create a binomial with them. That's not something you can do with two numbers. If I had 36 and 48 and I tried to add them, what do I get? I just get a new number, right? I get 84. It's no longer two terms. But these two terms, if I add them, makes a binomial, something new. Okay, so now if I take the GCF, which we already found was 2x to the 5th, there's something I can do with this binomial that I can't do with just plain old numbers. I can express this binomial as a product of a monomial times a different binomial. I can express this binomial as a monomial times a different binomial. What monomial am I talking about? I'm talking about the GCF. I can express this binomial as 2x to the 5th times some other binomial. Now, how do I find this other binomial? Well, I just took 2x to the 5th out of each of these terms. Since that's the GCF, I can do that. And the leftover will be whatever is left in these terms after I take out the 2x to the 5th. Now I'm using this phrase take out, but what I really mean is when I divide 8x to the 5th by 2x to the 5th, what remains? When I divide 6x to the 7th by 2x to the 5th, what remains? Okay, first one. I'll write the work on the side. When I divide 8x to the 5th by 2x to the 5th, what happens? The x to the 5ths cancel, and 8 divided by 2 is 4. That's what remains. When I divide 6x to the 7th by 2x to the 5th, what remains? Well, all of these x's cancel. 5 of these cancel, leaving 2 of them. And 6 divided by 2 is 3. So this is what remains. Now what do I have? I have, looking at me, the DNA of this binomial. The DNA of this binomial is this monomial, 2x to the 5th, times 4 plus 3x squared. What we've done is no different than taking some number like 35 and writing it as 5 times 7. This is the prime factorization of 35. This is the factorization of 8x to the 5th plus 6x to the 7th. And to double check, you could just multiply that 2x to the 5th back in. If that truly is the right GCF, and if this is the truly the correct leftovers, then you should get what you started with. 2x to the 5th times 4, 8x to the 5th, and 2x to the 5th times 3x squared, 6x to the 7th. I got what I started with. So this is the correct factorization. There's nothing stopping us from having 3 terms that have a GCF. So let's try that. Okay, I have 3 terms, and I'm going to try to find a GCF of the 3 terms in this polynomial. Each term has a coefficient, 9, -3, -27. The GCF of 9, 3, and 27 is 3. And now I look at the variable part. I have x cubed, x squared, and x. So the most that they have in common is x. So my GCF is just 3x. All right, so I know I can take out from these terms a 3x. Now, what remains? So I take 9x cubed, the first term, divided by 3x. What remains? 3x squared. I keep the sign. Next term, 3x squared divided by 3x, x. Next term, 27x divided by 3x, 9. So the factorization of 9x cubed minus 3x squared minus 27x is 3x times 3x squared minus x minus 9. Now you may feel like you're writing more when you write the factorization of this trinomial than the trinomial itself. Yes, that is true. Sometimes you are using more ink or pencil lead and time to write the factorization than writing the polynomial itself. But keep in mind what we're doing. We're not simplifying here. This is not simplification. This is factorization. Look at 35. It's quicker to write 35 than it is to write 5 times 7. 5 times 7, you're writing 3 things. So we're not looking for simplification. We're looking for factorization. And that means pulling things apart. Pulling things apart. So of course, factorizations will tend to be longer than the original polynomial that they come from. Okay, we'll do one more. I'm going to throw a second variable in it now. Okay, first coefficients, 8, -12, 4. GCF of 8, 12, and 4 is 4. Now I go for the x's. X cubed, x squared. The most they have in common is a single x. Now the y's. Y squared again. So is the GCF going to have a y squared? No, because the last one is just a y. So the most that all 3 have in common is y. Now for the leftovers. If I take 4xy out of here, I'm left with 2x squared y. If I take 4xy out of here, I'm left with 3 and y. If I take 4xy out of here, I'm left with just x. And that is the factorization of that trinomial. Okay, now I'm going to move on to something called a big GCF. This is my term. This is not the official term agreed upon by mathematicians. This is the term agreed upon by me, myself, and I. A big GCF is a GCF that has more than one term. how can a GCF be more than one term? Well, look at this. Okay, how many terms do you see here? And I want you to think of the big picture. There are 2 terms here because there are 2 clusters that have stuff that is multiplied. Here's the first group of stuff multiplied. Here's the second group of stuff multiplied. So 2 terms. Okay, now that we've established what the 2 terms are, do these 2 terms have anything in common? Do they have a common factor? The first term is x times x minus 1. The second term is 2 times x minus 1. You heard me say x minus 1 twice. So the GCF in this case is x minus 1. That's a binomial. So GCFs can be binomials.
Good afternoon, Longfellow. For all of our 7th graders that joined us today, let me reiterate again how excited we are that you've joined us today in returning to school. I want to explain our dismissal procedures for everyone again. So remember, you will be dismissed over the PA system. Please wait until your group has been dismissed, and remember, please exit the building right away so you can make sure that you don't miss your bus. So teachers, I would ask, please pull up the bus map that has been emailed out. And at this time, all 7th grade bus riders and Kiss and Ride students are dismissed.
Okay. Now you heard me say that the GCF is x minus 1. So what do we always do with that GCF? We put it first, and then we multiply it with the leftover. The leftover in this case is this x, which remained after you took the x minus 1 out, plus the 2 that remained after you took the x minus 1 out. Okay? So this is the leftover. This is the GCF. Think of it as one thing, and then the leftover had 2 things in it. So that's what a big GCF is. Now there's another situation where you might have a big GCF. But it doesn't, on the surface it may not look like a GCF. I have x plus 7 squared plus 5 times x plus 7. Again, I have 2 terms. And these 2 terms do have a GCF. Since the first term is x plus 7 times x plus 7, and the second term is 5 times x plus 7, both of those terms have x plus 7 as a factor. So I can write that GCF first, and then the leftover. But the leftover, you have to be a little careful, because is there a leftover here? When I take out an x plus 7, what remains? Another x plus 7, because remember, there were 2 of them here. So x plus 7 is the first thing that remains. And then from the second term, the 5 is remaining. Now what's interesting here is that inside this second set of parentheses, it looks like there's something that you can simplify. The 7 and the 5, 7 plus 5, and you must do that, of course, when you see the 7 plus 5. X plus 12 is what you get in the second set of parentheses. So again, big GCF, kind of hiding a little bit. You can still take the big GCF out, and then the leftover, in this case, had 3 terms in it, but 2 of them you could put together.
This time, all.
Okay? That's GCF.